This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Well, hello everybody, I'm Max Stevens and
I'm Duncan Simons.
this is our title today, How Can Computational Algorithmic Thinking Enrich Our Students' Mathematical Thinking? And we're looking at applications in number, pattern and geometry. Here's our abstract. This is a quote from the Australian Curriculum 2021 consultation draft, which outlines the definition of computational thinking. Notice those keywords: modelling, inquiry, problem solving in mathematics. Computational approaches involve experimental and logical analysis, empirical reasoning, and computer-based simulations. These aspects of computational or algorithmic thinking inform this session presentation.
And I think it's important that we do focus on the fact that we are using the revision because there are some clear changes and clear foci in the area of computational thinking that are now in the Australian mathematical curriculum that were not previously there.
Right. Here's the outline. We've talked about that. We will look very briefly at the revision document for the Australian curriculum. We will then present our pedagogical framework for developing algorithmic thinking in a way that links directly to mathematical thinking. And then we've got a number of important illustrations using Scratch, which can link computational thinking and mathematical thinking, utilising some important geometrical concepts which start in the primary school and extend into the middle years. Well, this is from the Australian curriculum, again, from ACARA. Those key elements of computational thinking: decomposition, abstraction, pattern recognition, modelling and simulation, algorithms and evaluation. It says computational thinking provides the strategic basis that underpins the central role of computation and algorithms in mathematics and their application to inquiry, modelling and problem solving in mathematics and other fields. The rest you can read through, but this is an important statement in the mathematics curriculum that hasn't been there before, as Duncan said.
And I think one thing to note, often when you see definitions of computational or algorithmic thinking, you see design thinking as part of it. And I actually think that what the Australian curriculum have done here is they've used modelling and simulation as a way of representing design thinking. Okay, so this is just a quick video. I'm sure many of you have seen B-bots before. However, this is just a demonstration that preps can indeed think algorithmically. You'll see that this prep is able to code the B-bot around the maze to the apple. Whilst this video is taking place, it's worth thinking about what this student is having to process whilst going about the coding process. She's had to keep a sequence in mind, which is quite an abstract process. All of those instructions were given, and then the execute button was pressed. So in some ways, that's actually quite sophisticated algorithmic thinking.
Here are our five key components of computational thinking: design thinking, decomposition, pattern recognition, abstraction and generalization. And we'll come back to these at various stages throughout the presentation. Just looking at the Australian curriculum again, some key points. The first point, helping students to develop their algorithmic, computational and logical thinking. Certainly not the same as memorising algorithms of the old kind that people might have been taught in mathematics. Algorithmic thinking is embedded in both the mathematics curriculum and in the digital technologies curriculum. The point we're making today, outlined in 4, is it's much more than coding. It provides students with a framework for problem solving and reasoning, and exhibits some of the key capabilities of the mathematics curriculum, or the proficiencies. It's the thinking behind the language, the kind of thinking that a computer would execute, and we want to see how that can enrich mathematical thinking.
And whilst it's sat within the area of number and algebra in the Victorian curriculum, I think the point that we want to make today is that computational or algorithmic thinking is actually part of all of the content areas and can really deepen and enrich students' conceptual understanding of those areas as well. Okay, so I'm just going to talk a little about how digital technologies and mathematics are linked through computational thinking. Obviously, there's a focus on data and computational and algorithmic thinking, but the things that mathematics and digital technologies really have in common are pattern recognition, data collection, interpreting that data, then representing it, and then and that can form the basis of a statistical investigation. So if you think about those key ideas, they really come from the statistics curriculum within mathematics. Digital technologies focuses on how digital systems represent data. So students are having to think about a broader system and then decompose that system in order to be able to understand how the digital technologies work, and they do a similar thing often in mathematics. It develops students' foundational understanding of algorithms in the early years, as we've seen. The implementation, design and creation of algorithms in mathematics form an integral part of a computational approach to learning and experimenting in mathematics. And it complements digital technologies and supports the development of computational and algorithmic thinking skills.
Okay. Well, here are some quotes from the Australian curriculum where it talks about computational thinking and geometry in Year 5.
Again, this is the revision.
This is in the revision document. You can see the reference to shape. So it's starting in Year 5. We might look briefly then at Year 6. You can see designing the second one, designing a set of instructions to transform a shape, including getting back to where you started with. We'll be looking at creating shapes. In the next, it looks at the effect of a robot. Then it looks at transformations and their applications. And in Year 7, again, computational thinking is about designing and creating an algorithm that will sort and classify shapes, creating a classification scheme for triangles, talks about flowcharts. We're not going to address these directly today. Our focus will be linking computational thinking with important aspects of geometry, but exhibiting the same directions and completing the same goals that the Australian curriculum talks about. This is our framework. So on the left we see computational and algorithmic thinking with those 3 key points: using an algorithm, modifying an algorithm, and using those experiences to create an algorithm. Now, that might take place in the digital technologies curriculum, as Duncan also said. But when we link it to mathematical thinking, there are these 3 other key points: narrating what's happening, what can be predicted, what can be generalised. Now, those 2 will interplay throughout our presentation, and we want to say that computational thinking can be used as an important tool for developing students' mathematical thinking using these examples in geometry. So let's go ahead.
Okay. We start with a really simple example, and we'll let you read through this example. You won't be doing it in this presentation, but feel free, obviously after the presentation, to go to scratch.mit.edu and have a play. We have the initial task of creating a square in Scratch with side lengths of 100 units. And then we start to question those elements of computational algorithmic thinking. How do we decompose this problem? What patterns do we need to be aware of? What mathematical knowledge is required? And what steps in Scratch will accomplish this? And I think as we move through the next slides, you'll see how we kind of go about that process. So here we have the code that you would see typically for creating a square with Scratch. This is very basic code. All it really shows is we put the pen down, so we've got a record of where our sprite, in this case it's the cat that most people see, is located. They move 100 steps.
So this is the narrating part.
Yeah.
What's the code doing? The students have to predict what will happen.
And at an early stage, they're not going to be sure what the units of movement are. So they're going to have to play around a little, I guess, with the number of steps. We then see that our sprite will turn 90 degrees. Wait 1 second, and that process will be repeated 4 times.
And we can see those 4 times in the blue in the Scratch code.
And for, I mean, the students, if we were doing this with a year 3 class or something like that, if we wanted to challenge the students, we'd say, why do you think that the 4 turns add up to 90 degrees, or a question similar to that? Okay. So there we see the code executed. We see the square, very simple, and we will move on.
So this is using our use, modify and create. So in the first case, the teacher could have given the students the Scratch code for drawing a square of side length 100 units. It's not necessary for the students to create that. Some may be able to. But the first step is to modify. Having done that code, how could we then draw a square of side length 80 units? What would stay the same in the previous code? What would change? So let's look at what's happening there. So that's the first modification.
Okay, so here we have creating a larger square with Scratch. So obviously we can refer to that as a similar shape. And we're at the narrate stage at this point. And if we look carefully at the code, we can see that we're now moving a greater distance. So each time, instead of moving 100 steps, we're moving 275 steps. So that is one thing that is different, that has changed about the code. However, what stays the same is the rotation. There's still only a 90-degree rotation because we do not want a different shape. We want the same shape, but we want it. We want a similar version of it. In this case, an enlarged version.
Okay. Okay, keep going.
It'll do another. Okay. Can't find my mouse. Okay. So after the narrate phase, we move to the predict phase. And yeah, we've just accidentally skipped ahead, but that's okay. You can watch this whilst I talk. What we want the students to do is to think about the variables that were included in the square and predict what other variables now that will need to change. And as you would all be aware, there will still be 4 90-degree turns. However, we now need 2 sets of parallel lines of different lengths. And these are key ideas in geometry. For students to truly understand the definition of a square versus a rectangle, they need to understand these sorts of terms because, one interesting thing is that in fact the square that they created before is a special type of rectangle. It's just got equal sides. Okay, so now we move on to creating a rectangle with different orientation in Scratch. Again, we are going to predict and narrate the changes that will need to take place. This time we are going to move 100 steps, turn 90 degrees, and then move 275 steps. So, and then that process will be continued.
So one of the things to predict there is what will this look like? How will this differ from the previous rectangle?
Yeah.
And we can predict, we hope, that this will have the short side on top.
Another question you could ask is, will the area of the rectangle be different?
And what stays the same? Notice we're using the blues. Each step is done distinctly, so you can anticipate that some people will be thinking about loops. We haven't addressed that yet. But there we are.
So this is very, very simple code at the moment, but there are some very, very important mathematical ideas happening. We move to creating a rectangle. Oh no, we've done that.
So here is generalizing. So we've had those different experiences, use, modify, according to the Australian curriculum. This is suitable for upper primary. We've looked at rectangles with different orientation. But what are the key mathematical ideas for moving forward? Well, behind all of this, of course, is 360 degrees. This is the complete rotation required for a rectangle or a square. Rectangles and squares require 4 successive turns of 90 degrees. Students might want to act that out in the classroom. This is needed for further work on triangles and other polygons, not the 90 degrees, but the constant 360. Multiplicative thinking is involved. The triangle will require 3 successive turns of 120 degrees. We'll look at that later. This is suitable for students who are ready, and provided students have had previous exposure, we can move on to drawing a triangle, drawing a pentagon, drawing a hexagon, and of course, what would stay the same, what would change for these 3 examples. So let's look at some of those, and of course, we'll also see how the use of Scratch can allow shapes that would be previously undrawable in the classroom using standard technology in order to draw out further some of these key aspects of mathematical thinking.
The other thing that I think that's worth noting is that students need to be aware that these are external rotations. They are not the internal angles within the shapes.
We'll see how that causes a problem later if you confuse the external rotation with internal rotations.
So here we have a triangle without a loop. And this does, as we'll note in a second, using loops requires students to identify and make use of patterns. You'll see the differences here between our rectangle and our square. We're still using 100 steps here, but we are doing that external rotation of 120 degrees. And of course, we're doing it 3 times. 3 times 120 is 360, giving us our 360 degrees of rotation. I think we'll move on. Okay, and this brings us to loops and why they are important to mathematical thinking.
Well, this is about pattern and relationship, isn't it? Loops rely on recognition and creation of mathematical patterns. And you can see the way that the Scratch program, the loop is a way of seeing that the blue codes have been repeated in the case of the rectangles and squares 4 times, in the case of the triangles. So a loop allows you to do that 3-step process with just one piece of code.
Potentially infinitely.
Oh, you can. And patterns and number are building blocks towards generalisation in algebra. We can talk about loops within loops, but let's illustrate how we can move into loops using Scratch and how that creates a simple code. But once again, the students have got to be able to narrate what is going on. So we could show them the code, and the code is embellished with the what Duncan is showing at the moment, the orange bit that's put around the blue bit, which talks about how far to move, how far to turn.
Yeah, so that bracket there is super important. That's the loop, and that is telling the sprite to execute the following commands 3 times. You can repeat it as many times as you like, but the fact that we're doing a triangle, 120 multiplied by 3 gives us our triangle.
Well, students might want to repeat it 9 times, and of course the loops will become redundant.
We've got a nice big triangle there, Max.
Yes.
Okay, and moving on to creating a pentagon within Scratch. Now, this is where I think it really, where the students' mathematical conceptual understanding will really show up, if it's there, that is. They'll need to realise that there's going to be 5 repetitions of rotations. They need to recognise that those rotations are external rotations, and that they need to realise that the 5 of those rotations will add up to the 360 degrees of the full rotation. So if they take their 360 and they divide it by 5, they'll get 72 degrees, which is the exterior angle of turn. Where the moving, however, doesn't change much. It remains 100 steps or units. But yeah, that code, that loop is really, really important there. We've gone from 3 to 5.
And let's see what that does. So the 72 degrees is how far the sprite turns. And that can be acted out in the classroom. On the floor, the shape could be drawn, and of course, having completed the shape, whatever the shape, the number of turn, the degree of turn will be 360. Well, here's a case where we're going to present a hexagon with bugs. This Duncan's idea and mine is that with computational thinking, we sometimes can present a problem code and say, what's wrong with this? Why isn't this achieving what we thought? So here's a case, it could be a student or the teacher presents this. Here's what's intended to be a hexagon. The six loops
Is correct.
But what's different? Well, the distance is specified, but in this case, the degree of turn is specified as 120 degrees. So as Duncan said before, this is confusing the internal and the external angle of the hexagon. So let's predict what the new code will result in. Let's observe. The student thinks this is going to form a hexagon, but let's see what happened. It's not a hexagon. It's simply a triangle. So the question is, what would we need to do to that code? What would we need to change in order to create a hexagon? So this is debugging. We see this as an essential part of working with computational thinking. We all make mistakes, but the mistakes can be enlightening. In this case, we didn't draw a hexagon because we didn't think of the degree of turn correctly. So in the debug, what had to change? What stayed the same? This is important for teachers to present students with non-examples, e.g. a faulty code that must be debugged. While this whole process and inquiry, computational thinking always requires debugging and modifying, which at times will require explicit instruction on the part of the teacher.
Yeah, and I just wanted to emphasize the fact that this whole process that we're going through at the moment is inquiry, but it's also highly teacher-led and directed. So it's a really good example of how inquiry learning in mathematics can be a really engaging and really deep learning experience.
Well, with well presented and well crafted examples that form the basis of direct instruction here. Okay, so that's debugged. Now we go on to some more interesting steps. We can think about this is a hexagon. Each time it's completed, you can see what happened. This is beyond primary school, but some students will be able to explore this use of creative patterns. It is working.
Yep. And what we've done is we've also jumped to a more sophisticated coding type. Obviously, this is text-based code. This is Python. So this is probably, you would expect to see this in secondary school rather than primary school. Just a couple extra things. We have a loop within a loop, which is essential to this process occurring. Let's have a look at it. And while you're having a look at it, think about the mathematics that students would require in order to create a program such as this.
So they've got to understand the basic components of drawing a hexagon, but in this case, each hexagon, when completed, the new starting point moves forward by a rotation of 10 degrees. So in this case, we're going to have 36 hexagons drawn, which form this rather beautiful pattern.
Yeah, I think it's a great example of how mathematics, geometry...
And students are going to talk about the apparent circularity of the resultant shape, and so on.
Yeah, there's so much interesting stuff happening there.
We've got about 10 minutes left.
Okay.
Now, this is, of course, the third part of our mathematical thinking. This is the generalising and extending. So this is important. These are exercises for teachers to build confidence in and mathematical thinking in students. Here are some examples. Now, having done triangle, pentagon, hexagon, we can move on in ways that were previously very difficult. We can look at a 20-sided figure, all sides equal, 40-sided figure, all sides equal, a 100-sided figure, all sides equal. Now, we can predict again what would be the degree of turn. 20-sided figure, yes, 20 divides into 360. 40-sided figure, that divides. But a 100-sided figure doesn't give a whole number result. Now, that's really very, very interesting. We've never done decimal degrees easily with conventional instruments.
No, our protractors don't have decimal degrees, do they?
Exactly. But this is all possible when we're using code. So what stays the same? What modifies? And here we use the third part of our computational thinking model. This is the create part.
Okay, so students at this point take what they've learned about the polygons, as Max was saying. I think we can sort of move through this.
Well, let's go do that directly. Okay. Yes, we're doing well with time.
Yep. So did you want to go through this, or shall we move forward?
Well, Sarah says that 100 sides could be a problem. Well, no, 100 does divide into 360 and gives 3.6 degrees.
Yeah.
Predict as the shapes increase their number of sides. So what are we doing here? We've got a 20-sided figure. Notice that we've had to change the side length. Well, the sprite is drawing a very interesting 20-sided figure.
We could get the sprite to draw a 50-cent coin for us, Max.
We could indeed.
Yep. And that would be a good question for your students. What would you have to do in order to create a 50-cent coin?
So here again, we're looking at a 40-sided figure, a tetracontagon.
Tetracontagon.
Okay, what are we seeing? Well, the turn is 9 degrees, and the number of steps. The number of steps, of course, can't be 100. And of course, some students might look at the previous code and write 100 steps in. It's not going to look very good on the screen. So that's another necessary part of debugging. So let's look at what happens with the 40-sided figure. Here's the sprite moving around.
I noticed that I also decreased the number of wait time in between the sprite's movement, and that's because if we were waiting 1 second for every side to be moved, we'd be waiting there for 40 seconds, and it seems a bit much.
Now, of course, some children will say the sprite's drawing a circle, but we need to talk about magnification. Of course, in this small screen, it might look circular, but there are, in fact, 40 sides. That's what we've asked it to do. Mm-hmm. And, of course, if we could zoom in to the screen, we would see that they are distinct sides. But here's a 100-sided figure. Once again, what can we predict? What will be in the code? Well, you can see here that the rotation is now 3.6 degrees. This is multiplicative thinking. This is an exploration, very simple in Scratch, but would not be able to be achieved in our conventional geometry classroom, well out of range.
Yeah, and we get to see the effect of multiples of 10, 100, 1000 with this sort of activity.
Correct.
They could easily move from this to creating a 1000-sided figure if they just obviously turn 0.36 rather than 3.6. And as you can see, it looks very much like a circle, but it is not, in fact. And then a question you could pose to your students is, what would the instruction have to be to my sprite in order to make a true circle?
Right.
And that would be pushing them well beyond their comfort limit, I think. But the loop would have to be infinite. Yeah. Let's move on, shall we?
So here's our summary slide. And I think this is drawing us to the end of our presentation, where we say, how does computational thinking link directly and support mathematical thinking? Even in these very simple illustrations using Scratch, you can see important uses of multiplicative thinking and proportional thinking. They're elements of measurement and design, where we have to think about step length. How do we adjust step length for the different sizes of figures? Coordinate geometry is important. Whole number and decimal angles, particularly decimal angles, become possible. But certainly fractions or proportions of 360 degrees. Now, drawing a 7-sided figure is not going to give you a whole number of degrees, but that can be specified in Scratch quite easily. This builds understanding of base 10 system, the various ways in which 360 can be represented as different multiples. Where previously we wouldn't have thought to measure and express and use angles in decimals, we can do that easily for the purpose of using and generalizing shapes. At all stages, we have to emphasize what stays the same, what varies as we move through. So in the different programs, of course, some without loops, but even within a loop, what stays the same, what varies. So the link here between computational thinking, geometrical drawing, and generalization becomes possible using the different advantages that technology provides and ideas of proof. Our two elements of mathematical thinking and computational thinking: use, modify, create. This is an element that can be used at primary school, secondary school, university. Using a code that someone has given you, being able to modify the code in order to understand how it works, and then with that confidence creating a code that will allow you to achieve a different purpose. finally, narrate, predict, generalise.
Yes. And I think generalization and proving are often difficult in a primary setting. I think that the process that we've just been through with you should support your working towards that. And what we're really doing is giving the students a much deeper conceptual understanding of those geometric concepts. That just isn't possible with the instruments that we previously might have used.
So, as distinct from what students might be doing in digital technologies, here we're now using the affordances of computational thinking and scratch coding to see how can we develop the specific mathematical skills that underpin our children's learning and that are recommended in the Australian curriculum. So at this point, we would stop the presentation. We've had some questions on the chat, but we'll have now 10 minutes for questions and comments from people. Thank you very much.
Thank you very much.
Well, I think that's pretty good. Right on 35 minutes, Duncan.
And then I just have to
Stop recording.
now we have.